Hello, we are Team BRACU Mongol Tori. After nearly a year of development, innovation, and testing, we are delighted to showcase you our rover, Pheonix. Here we will be showing you how our new and improved rover is equipped with completing the tasks for URC 2024. For the extreme delivery mission, our rover is equipped with high traction material on its wheels to handle rough terrain. Along with this, the rover has a rocker-bogie suspension mechanism that allows it to traverse through harsh and rugged terrain. It is able to go over and cover up to 35 centimeters of rocky terrain. Our user-friendly GUI displays the rover's position and orientation data, giving us the ability to traverse to long ranges with a given set of coordinates. Having learned from our previous iterations, our new dual-band communication systems in 2.4 and 5.8 frequency bands allows for stable and long-range communications. In case the 5.8 GHz band goes out of range, the system will automatically switch to 2.4 GHz band to ensure stable network connection. This whole system provides up to 700 meters in range. Our newly developed power distribution module is in charge of supplying power to all systems, allowing for ease in powering the rover as well as stopping all systems in times of unexpected behavior. Our rover is fitted with a new 5-degree freedom manipulator. This new manipulator has most of its weight concentrated at its base, allowing for a greater payload to manipulator weight ratio compared to our previous robotic arm iterations. This new lightweight arm has a payload strength of up to 7 kgs for pick-and-place operations. The new arm is also fitted with prismatic joints and revolute joints on its end effector, allowing for precise, linear movement without any arbitrary axis. The inverse kinematic model allows for assisted human-robot control of the arm, making the time spent on going from one position to another much less, allowing for the user to make more time for intricate manipulation of the arm. An omnidirectional steering mechanism has been implemented on our rover, allowing for different modes of steering and locomotion. Our default motion mode is set to skid steering. We are also able to choose between strafe motions and omnidirectional motion. The strafe motion allows for large, reliable movements about a single linear direction without rotating the entire rover during the equipment servicing mission, while the omnidirectional mode allows for large, smooth, reliable rotations. For autonomous navigation, we are taking full advantage of the ROS navigation stack, configuring the move-based node according to our rover specifications. Use of move-based will allow for dynamic obstacle avoidance while traversing paths from point A to B. A custom global planner is also being developed in efforts to implement our own path planning algorithm. A differential GNSS is being used for more accurate positioning. Odometry data is being taken via the sensor fusion of a military-grade inertial measurement unit and the GNSS module. Both the IMU and the GNSS data is being streamed through an extended Kalman filter, allowing for more accurate and reliable data to be received. Our web GUI has been made such that clicking or searching for a set of coordinates on the map will publish the coordinates to the navigation node. This allows us to easily publish multiple points while also being able to receive feedback on the rover's position on the map. The onboard computer in Intel NUC has the YOLO V8 deep learning model, which is trained on images of orange rubber mallets and 1-liter water bottles of different brands, including international brands, for a wider range of usability during the mission. The rover is equipped with an Aruko detection model to help detect AR tags at long distances. Search patterns have also been implemented on the rover to help detect AR tags if not found on first attempts. The science mission is being tackled this time with the use of a custom-built light spectrometer. The spectrometer will use UV and visible light spectrums to analyze the present biomarkers in a soil sample, such as flavin mononucleotide, porphyrin, and iron-sulfur clusters. The spectrometer is fitted with cuvettes arranged in a circular holder that will rotate to enable us to fetch readings one after another. Given that our desired biomarker is present, its concentration can be quantified by measuring its intensity and using Beer-Lambert's law. An hydrogen test will also be used to find the presence of proteins. We will also be using a conductivity meter to measure the salt content in a given sample. A temperature and NPK sensor will be used to analyze and monitor temperature, nitrogen, phosphorus, and potassium levels present in the soil. A modular wet lab has been integrated onto our rover to carry out these chemical tests on board. All of this data will be displayed on our web GUI, and continuous data will be saved in a CSV file to allow for graphical representation. This will all be used to interpret the presence of dormant, extinct, or extant life on the samples. This entire module is fitted with a dedicated 2-degree of freedom manipulator, which will be able to take soil samples from 10 centimeters below the ground. We have also equipped the onboard computer with an AI module to detect rocks and the types of rocks they may be. We, Mongol Tori, are very excited to compete and wish all the teams the very best. We hope to see you all in Utah.